Welcome, everybody. Thank you for joining our MIT Inside Track session as part of EmTech Digital. I'm Reed Sturtevant. I'm a venture fund put into business by MIT. We invest in tough tech companies that are working on some of the world's biggest problems. I feel fortunate to have Alex Wallar with us today. Alex is CTO and co-founder of the Routing Company. Alex, welcome. You were recently working on a PhD at MIT's Computer Science and AI Lab. Can you tell us about your connection to MIT, maybe something about the lab and the research that you were doing there?
Yeah, I got accepted to the PhD program in 2015. And so I went originally to study robotics, and I had experience in doing multi-agent path planning. So just actually how robots are moving together. And I was fortunate to become part of this project in the lab to optimize on-demand mobility systems. We were essentially trying to solve the Uber pool problem, but at city scale, in real time, to optimality, and using buses instead of passenger cars. We eventually published a paper that showed we could service all of Manhattan's taxi demand with 80% fewer vehicles by having the passengers share rides. After we published this, it seemed to us that the remaining effort to move people from A to B was no longer academic, but was in operations, business development, engineering, and product. And so that's why in May 2019, I decided to leave my PhD, and my co-founder decided to quit his job and move to the States. And we founded what was then called Routable AI, now called the Routing Company.
That's great. So tell us a little bit more about the New York City taxi simulation or analysis, because to be honest, that sounds kind of unbelievable. I mean, if you're sharing rides with other people, isn't it like you're taking an airport shuttle where your hotel is always the last one? You know, if you take that many cars off the road, would the quality of the trips suffer?
No, so that was the amazing part. You know, if everybody's willing to wait forever, then you can service, all passengers with, one vehicle if everybody's willing to wait forever. But it's how do you do it in such that you are maintaining the quality of service. So in the Manhattan simulation, we found that while servicing all the passengers with only 3,000 cars, even when you shared, we were able to get the waiting time down to less than 3 minutes for an average waiting time, and an average delay of less than 6 minutes.
That's amazing.
Yeah, it really didn't impact the customer convenience. It wasn't very different than going directly from A to B. So that's what I mentioned when I said the delay of 6 minutes. The delay we use as a metric to say what's the difference between me going from A to B just directly, or me going from A to B while sharing with other people. And so if you're only going to add 6 minutes in total to your commute by sharing with others, it's not that big of a hit in terms of shared mobility.
Mm-hmm. That makes sense. And then when you are doing the optimization and trying to make fit which vehicle should pick up which rider and drop off where, maybe change in the middle of a route to add another rider. How does that fit into AI? I mean, most people think of AI as training data, machine learning, and inference. Kind of, how do you consider yourself part of that optimization part of the world of AI?
Yeah, I think that we have a tendency with AI to put fields of study or projects into boxes when we try to define things as AI. But AI is, generally, and I, Googled this online in preparation for this talk, but it's about using computers to make decisions that would normally require human intelligence, and having that computer make those decisions faster and at scale. And I think the way we fit into AI with our optimization is that previous approaches using optimization were either heuristics, which meant that they did not give you the optimal result, or they were put into a commercial solver. You modeled your optimization problem as a big X plus Y equals 1 type of problem. You throw it into a commercial solver, which are off-the-shelf optimization solvers that you can use as long as you formulate your problem in a specific way. And then you formulate your problem that way, you press enter, and then you wait for a result. And that just took too long, especially at city scale, and especially to compute in real time. So in terms of being able to assess more routes than a human could possibly do, and to do that in real time faster than any computers, really puts our optimization within that realm of AI definitions. We are making it so that a computer can make these decisions better, more optimal in terms of which vehicle is going to pick up who. And we're doing that at a scale that humans couldn't possibly do.
Mm-hmm. I in prep for this call, I went back and read the paper that we've been talking about, and there's some jargon in there that I found interesting. It made me start thinking about time as an element, not just the optimal, one answer, but how long you're willing to wait for what kind of quality answer. And there was a phrase that was in the paper called anytime optimality as a character of the algorithm. Can you talk us a little through that concept?
Yeah, so anytime optimal just means that if I'm running my algorithm, and the longer I run it, the better the results will get, right? And so it's very similar to machine learning when you're thinking about training data. So if I let my neural net sit and train for 1 hour versus 10 days, you're going to get a different result. What anytime optimality means is that if I cut it off and stop the optimization anywhere while it's computing, I'm going to get the best current result. And so that means that you typically get an answer very, very quickly, but if you give the solver more time, it will find better and better answers for you. That's the idea of anytime optimality.
Mm-hmm, mm-hmm. And is that now that you're actually building a company and as services? I know you folks recently launched in Houston. How do you turn the dial in terms of user experience? It's like I love the idea that you can stop improving the answer anytime you want, and you'll get the best answer up to that point. But how do you in the real world, how do you set that dial, or kind of talk through about the choices you've had to make in implementing it as an actual real world tool?
Yeah, so in terms of a real world tool, we really have 3 dials that we can touch. There's many more, but like 3 of the main dials. One dial is the timeout, so how long we're going to allow our solver to be finding new solutions. The idea of anytime optimality, when's that cutoff time? That's one of our knobs. And then the other knobs have to do with the user experience. So that's the maximum waiting time and the maximum delay. So these 2 quality of service constraints that we utilize when trying to determine which routes are feasible. And what's interesting is that all these knobs affect the optimality and the performance because they all interact with each other. So the timeout knob, if I set that to be very low, I'll get a very, very fast response. But it may not be the best allocation of routes for these vehicles to service some set of passengers. Similarly, for the max wait and max delay, if I set the max delay to infinity, right, we could have one vehicle pick up everybody, but that's going to lead us to likely more rider cancellations. Well, it definitely will lead us to more rider cancellations than we would expect otherwise. So it's about fine tuning such that we can be returning results to the customer in terms of, to the rider in terms of their routes fast enough. Right, and so what do we deem as fast enough? Do we deem 30 seconds? Do we deem 5 seconds, 1 second? It really depends on the level of demand in that area. Also, using the max wait, max delay allow us to make the possible set of options more sparse, which can can reduce the time it takes to compute them, but you may not be able to service everybody. So you also have to be balancing out what percentage of your incoming demand are you servicing. And so then you have these 2 knobs that you can continuously turn so that you can hit your key performance indicator for your service rate. Say you want to hit 85% fulfilled, but you also want to be responding to users in real time. So you need to have it under 1 second, and then you can adjust the max wait, max delay to meet your needs.
Mm-hmm. That's fascinating. Would as you were working on the general problem, maybe before turning it to transportation, I'm sure we have a wide variety of industries that the audience works in. This whole general problem of optimization, where else do you see it crop up in the real world? Yeah.
So interestingly enough, we when COVID hit, we decided to spend some of our resources helping out this program called the Boston Healthcare for the Homeless program that needed an optimization software for for allocating beds and reassigning them in a field hospital. Didn't end up coming to fruition, but it just shows one example. Of where optimization can be used. Anytime that you are able to model a problem, like you don't need to use neural nets in it for everything where you can actually make up a model. If you can really formulate a model for your problem, then putting it into an optimization solver is a really good way of getting very, very high quality solutions to problems that would be very, very hard to solve otherwise.
Mm-hmm. I like the example of allocating beds in a hospital, sort of resource constraints and how best to use them, whether it's cars and then quality function like length of a ride. You raised COVID-19 and the pandemic. We have a question from Emile Delcourt. What was it like to work on a business that puts people together during a pandemic? So sharing rides, kind of any thoughts or experiences on that?
Yeah, so it's been difficult. So on one hand, there is really a dire need for ways to augment public transportation currently, just given the pandemic. With the budget cuts in public transportation, it means that fixed route buses, they're being cut, a lot of them, to save money because they're not getting that same fare box revenue from these buses, the transit agency. And so they need dynamic on-demand systems to service, and to maintain accessibility of their transit network. However, yeah, you're right that putting people together in a small vehicle is not ideal for the coronavirus. What we've done in Houston for our launch is our vehicles have separate doors for each passenger, and there is a partition between the seats, so there can be some separation. Also, we only allow 50% of the passengers to enter the vehicle, so the vehicles are never running at capacity. And through that, we have seen people are open to sharing rides with others, given those constraints at the moment.
Mm-hmm. It sounds like the routing company is definitely working in support of the public transit authorities and municipalities, rather than as taking business away from them. Is that fair to say?
Yeah, at our core, we partner with cities to power the future of public transportation. We really want to work with cities in order to increase their accessibility of public transportation. Buses are not huge moneymakers, right? The unit economics of a bus are not fantastic, and that's because we are subsidizing them, because public transportation is really meant for everybody and not just those who can afford it. Yeah.
And as the results of your successful optimization approach, the whole idea of reducing the number, serving the same number of riders, same quality of experience, but with way fewer vehicles. Can you talk a little about, as a public good, how does that make people's lives better? What are the different outcomes? If you succeed at scale, how is the world a better place?
Yeah, our vision is that a community of any size and anywhere with any amount of resources can meet the transit needs of its people. And we really don't want people to be blocked by their access to public transportation to access, the economy. We don't like right now, if you live in public transportation deserts, even in big cities like New York City, it increases the chance that you're going to need to own a car. And once you own a car to get to work and you're not earning a ton of money, right? If something happens to that car or something happens to your access to transportation, that can really leave you in a horrible spot where you can't earn any money. And so I really think that the routing company is going to make it so you can live anywhere in a city, but still be connected to your place of work and to places that are selling things like restaurants and other parts of the city where there is economic activity. You shouldn't be blocked access any type of economic activity because of public transportation. It should really be accessible and easy to use and to get you anywhere that you deserve.
Mm-hmm. And talk to us a little bit about, as you come out of your, doing research as part of a PhD program, and now turn to building and launching a product in the real world. The theme of this year's EmTech is the age of implementation. So what has it been like for you and your team to build this as in your own personal age of implementation? Can you take us through some of that experience?
Yeah, so the first thing, it's been really amazing for me. Being a CTO, having this come out of my PhD, it's all been theoretical, all hypothetical, has been simulations until we've launched in Houston, which makes everything become real and the problems can change. So, for instance, and this happens a lot, that there's interaction between user experience and optimality. And you would think, well, it's just an algorithm, just optimize it and get better results. But sometimes that depends on the user as well. So for instance, we had this issue where riders were canceling, like a lot. And we had no idea why. And we looked through the logs and we find that people would cancel, then request again, then cancel a ride, then request again. And we found out that it was because our progress bar on our app looked like there was going to be no time remaining after you requested your ride. So people were preemptively canceling it, even though they might have been assigned a vehicle. And that caused our fulfillment rate, our service rate, which is our most important KPI to decrease. And it turned out, to actually get people from A to B, we have to create the user experience that makes them think that they're going to get assigned a ride and then be taken somewhere. So it's just interesting how the real world and user experience and how, you're building an incredibly intelligent, optimization engine, right? But at the end of the day, somebody's just clicking a button and then a car is picking them up. Anybody should be able to use this. And that's, the interesting play between how good can you make something and how you can make the experience. It's just quite interesting, the interplay.
When you saw that anomaly in your logs, what was your first intuition? Did you think it was something wrong with the core?
I thought it was engine, I thought there was a big bug, and I was very, very, very worried until putting myself into the position of the user, and then I could see like, oh, I would probably cancel this if I reload pages when they don't load fast enough on my computer. I definitely do the same on my phone, and so I had to move myself away from why is this happening because of the back end and our optimization engine, and had to move myself into the perspective of a user. Why is this happening? Because of the user experience. And when I had that thought, it became pretty clear.
Back when I was doing product, we would call it fun with humans. You never really, unless you sit and watch over someone's shoulder, you really don't quite. And then it hits you in the head. Oh, of course, yeah. Yeah, exactly. Yeah, that's funny. Is there and going forward, what are you thinking in terms of the core technology in the challenges that are ahead of you? Yeah,
so I think originally we were the company that you could press a button and get a shuttle bus, right? Mm-hmm. And that was our MO. I think we're going to be moving from that to push a button, get a transit service, get a transit system. Mm-hmm. And we can build. I want us to optimize and co-optimize the design of transit networks with existing public transit options, including subways and buses, alongside on-demand systems, because all of these systems interplay. And how good an on-demand system will be in a very dense city is dependent on the other modes of transportation and how people are moving around in that city. And so there has to be some type of co-optimization such that you can be a transit leader, you can be the CTO of a transit agency, and you can go to a website, you can upload information about your existing routes, and you should be able to get a plan for how you can best optimize and introduce modalities to optimize your existing transit network. And that's where I think we're going to be going in the next 5 years.
Mm-hmm. That's interesting. So it sounds like you're describing a way to help, let's say I'm a municipality, help me understand how to design a system based on historical data.
Yeah, historical data and the current existing infrastructure, right? A fixed line bus that is at capacity every day driving down a boulevard is doing a very good job, right? So how do you increase the reach of that network? How do you compose the on-demand services with the fixed line services and provide an all-in-one, out-of-the-box transit network product?
Mm-hmm. That makes a ton of sense. I see a couple questions from the audience. Here's a question from David Vismans. Is the rideshare problem a variant of the traveling salesman problem? If so, are there other real-world problems that kind of also map into that problem space?
Yeah, so the Uber pool problem is a variant of the dial-a-ride problem, which is a variant of the vehicle routing problem, which then comes back to the traveling salesman problem as that original type of optimization problem. And yeah, other problems can be mapped to it. The way that we solve the problem, and I'll just go back a little bit. The way we solve this problem for matching riders and drivers and creating routes for the vehicles is very, very different than has been done in the past. Instead of using this one big optimization engine and then throwing in your constraints and your integer formalization, we instead break the problem into two parts. So we have a specific type of optimization system that's best at optimizing the sequence of pickups and drop-offs that a vehicle will make to service some set of passengers. And then we have another optimization step that then selects some subset of those pickup drop-off schedules to minimize a global cost function. So it's like this two-step approach. And so where I think this approach could work really well in other areas are scenarios where you need to sample some very large space and then select some subset, right? As long as you can optimize the generation or that sampling step, right, then the selection step can actually be very, very easy and fast to solve. And so what we spent a lot of our time doing was optimizing that sampling step, right?
Interesting.
Given the vehicles and the requests, how do we can generate all of the possible options or all the possible good options that we use.
That's helpful. And then another question, maybe the last one. David Tyke, as you and your website mentioned Houston, are you able to talk any more about any other communities that you're working with or planning to work with? And I'm not sure what you can share as a company.
Yeah, so we have a couple of deployments that are upcoming in more rural areas with lower numbers of vehicles and farther travel distances. We find it to be a really interesting problem because those folks tend to be extremely underserved and lack options for transportation. And so, yeah, because in the beginning we were talking about these constraints and the quality of service and the maximum wait, maximum delay, all of these can be tweaked for the different densities, such that we can have a service that can accommodate what the expectation of a Manhattan traveler is versus the expectation of a more rural traveler. A Manhattan traveler with a really high density would probably expect a vehicle in 3 minutes and 5 minutes, whereas a more rural traveler would be willing to pre-book or to book and then wait for 30 minutes to get picked up because the alternative to that was no options.
That's interesting. It's a pretty broad span of applications of your service. It sounds like, and it sounds like a real issue of social equity and social.
Yeah, in rural areas, a lot of times people only have one car for a household, and so when that car, overseas particularly, and when that car leaves the household, the people at home have no way to get to the city center besides very, very unreliable fixed line buses.
So we're coming up on time. This is a fun conversation, Alex, and it sounds like you're really working on something that matters, using some pretty difficult and sophisticated software in the AI space. So Alex, thank you so much for taking the time out from your startup to talk to us. And to the audience, thanks for joining this session. Hope you enjoy your next EmTech session. Thanks so much.
Thank you.